Well, now that we have demonstrated that a transmission line really consists of a guided electromagnetic wave consisting of electric fields and magnetic fields, in this lecture, we are going to show that the electromagnetic wave can still exist even if there were no conductors and there were no transmission lines, meaning it can exist in empty space. And we're going to start by studying the simplest form of radio wave, which is called a plane wave. This lecture is divided up into three sections. The first, we'll talk about the plane wave in the time domain, then we'll talk about it in the frequency domain, and then we will generalize to plane waves in arbitrary direction, which makes the math slightly more complicated, but is more useful in general. Let's start with part one, plane waves in the time domain. So we're going to introduce something called a uniform plane wave. A uniform plane wave consists of the following. Right, let's imagine that we have a source somewhere, maybe an antenna, something that is generating a radio wave. Probably has some current on it. That's the primary way to generate a radio wave. And we would expect a radio wave to sort of emanate in sort of spherical shapes coming out of that, much like dropping a pebble into the water, and you get sort of a circles that expand outwards from that. And so we're expecting basically these circles roughly to correspond to the edge of the radio wave as it propagates. And if you can imagine continuing on until you're really far away from the source, eventually you reach a point where you're so much further away from the source than you are the size of the source itself. And when you do that, basically this surface right here can be treated as very close to flat, right? It's a little bit like saying if you're on the surface of the Earth, if you're only looking over a 100-foot by 100-foot square, you don't actually realize that the Earth is curved. It looks pretty darn flat. You have to sort of see a much bigger part of it in order to see that the Earth is curved. And so that assumption is basically what we're going to call a plane wave. Right? We're making the assumption that over a plane, nothing is going to vary. Everything is the same. Right? So that assumption is called plane wave. A uniform plane wave adds the fact that nothing is changing along this plane, right? Which means if we're gonna define a coordinate system to start out with like this is going to be the x direction. This will be the, that'll be the z direction. This will be the x direction. Y is coming out of the page, since x cross y must equal z. And we can say that all derivatives in the x direction equals 0, as is any derivative in the y direction. Things can only vary in the z direction. So that's what we mean by uniform plane wave, is this d dx equals d dy equals 0, right? We're also going to add a couple other restrictions. We're going to call the material that this propagating wave is going through, we're going to call it a simple, right? Simple media. That basically means a couple things. It means that the material properties mu and epsilon are constants. That means there are no boundaries between two materials. They don't change with time. They don't change with frequency. They don't change with the electric field or magnetic field quantity. They are constant. They also don't change with direction. They're just numbers that never change. We're also going to treat something called lossless media. And we'll see what that means later. But that's effectively going to mean that there is no conductivity. And that rho v equals 0. There's no charges. And we're also going to be able to say that J equals 0. There's no current. All right. This is going to be our starting point. We're going to take away some of these restrictions later, but this is our starting point. Uniform plane wave, nothing is varying in the x or y direction. We're going to assume we have propagation in the z direction. We have simple media, which means that mu and epsilon are constants. We have lossless media, which means no conductivity, no charges, and no current. All right. So let's review Maxwell's equations before we determine that a wave comes out from this. And let's just write this down. that the divergence of D equals rho V, we can set that equal to 0. We can go one step further because since epsilon is a constant, we can pull the epsilon out of the divergence equation, and this becomes epsilon times the divergence of E equals 0. All right. The divergence of B equals 0. We're going to do the same thing. We're going to pull out the permeability because B equals mu times H, just like D equals epsilon E. And we're going to rewrite this as mu times the divergence of the magnetic field equals 0. And we're going to do the same thing with the other two equations, that the curl of the electric field is negative dB dt. We'll rewrite that as the curl of the electric field equals minus permeability times the time derivative of the magnetic field. And finally, curl of H equals time derivative of the electric flux density plus J. But in this case, there's no current. So we're going to rewrite this as the curl of the magnetic field equals epsilon times the derivative of the electric field with respect to time. All right. So these four equations on the right are the key ones we're now going to use. This is Maxwell's equations recast for the simple and lossless media. All right. And let's try to use Maxwell's equations to derive what we're going to call the wave equation. All right. Now, the wave equation, as you may recall, told us that if we have two quantities A and B, that the second spatial derivative of one equals the second time derivative of the other, and vice versa. The second time derivative of the first one is proportional to the second spatial derivative of the second one. And we're going to use Maxwell's equations to show that that is in fact the case here as well, right? And the way we're going to do that is we're going to start out with this curl of E equals minus mu times the derivative of magnetic field with respect to time. And we're going to take the curl of both sides. So this becomes the curl of the curl equals the curl of this whole thing right here. It turns out there's a quantity that tells us that the curl of the electric field equals the second spatial derivative, or the vector Laplacian of the electric field minus the gradient of the divergence of the electric field. And we also know from the first of Maxwell's equations that this divergence of E equals 0, since there can be no charge. So this whole term is gone. And so we can substitute that in. I'm going to keep that in black. That the second derivative, or the vector Laplacian of the electric field, is equal to negative mu times the curl of dH dt, but we can also pull out the d dt since that's a linear operation. So this becomes negative d dt of mu times grad cross H. All right. Now from here, we can now substitute that the curl of H equals epsilon times dE dt. So the second spatial derivative of E equals minus d dt. Let's pull the mu over here and substitute. This is going to be an epsilon times dE dt. Let's carry that on a little bit further. We can combine the two time derivatives into a double derivative, and we can pull the epsilon back out. And here we got grad squared of E equals minus epsilon mu times d squared E dt squared. All right, now this is called the wave equation. The only assumptions we have made is that that simple and loss-free media is what we're dealing with. And again, this second derivative of the electric field, this is a spatial derivative. So this is like saying that the second spatial derivative of E is proportional to the second time derivative of E. And that's exactly our definition of the wave equation. All right, let's see this bear out. And in order to simplify this, I'm going to apply some of the other simplification that we made, namely that we have propagation in the z direction, and we have all of our derivatives in the x and y direction are 0, in which case we can simplify again. So let's see how that's going to play out. Right. The second spatial derivative of E is going to be grad squared of EX in the x direction plus grad squared of E in the y direction plus grad squared E sub z in the z direction equals minus epsilon mu times d squared E dt squared. And furthermore, we can also assume that because the x and y derivatives are non-existent, we can simplify this into the following, that the second derivative of the x component of E with respect to z equals negative epsilon mu times d squared EX dt squared. Right, so by assuming that d dx equals 0 and d dy equals 0, we can reduce that above equation to this one, right? And here, this is exactly our definition of a wave, that we have a quantity, E sub x, and its second spatial derivative is proportional to its second time derivative. And that's the definition of a wave. And we know the general solution to this is going to look like this. It's going to be EX equals E0, some constant, times some function t minus z over Vp plus E0, right, okay, let's not put the z, it's 0. Plus there's another term here, which I'm going to leave out, but this represents the positive going wave. Furthermore, we can show that Vp equals 1 over the square root of mu, the permeability, times epsilon, the permittivity. This is equivalent to the equation that we had in transmission line days. In transmission line days, we had that the second derivative of voltage with respect to distance equals negative L times C times d squared V dt squared. And from that, we said that Vp equals 1 over square root of LC. So we're at basically have the same thing for radio waves, except instead of an L and a C, we have an epsilon and a mu. So Vp equals 1 over the square root of mu times epsilon, right? So we can already see that there's a defined propagation velocity, and that propagation velocity is dependent specifically on the material properties. We can also determine that there is a impedance. We're going to call that eta, and we're going to see a lot of eta. And eta is going to be the square root of, instead of having an L and a C, we're going to have a mu, the permeability, divided by epsilon. And this does, by the way, have units of ohms. What that is basically telling us is that the magnetic field in the y direction will turn out to be E0 divided by eta times F of T minus C over Vp. That the ratio of the electric field to the magnetic field is precisely equal to this quantity eta, where eta is the square root of mu over epsilon, and it also has units of ohms, just like the Z0 that we had in transmission lines. All right. Now you might be saying, hey, wait a minute. If the electric field is in the x direction, how did I know that the magnetic field must be in the y direction? And so that we can get from Maxwell's equations, because we know that time-varying electric fields are going to have magnetic fields wrapped around them, and time-varying magnetic fields are going to have electric fields that wrap around those. And so from this equation, you can plug in what Ex is, and you can use these two equations to then solve what is H, and it turns out that H has a Y component. It's the same process we did in the last video to get from the magnetic field generated by a current to the electric field using these two Maxwell's equations. But if you do that, you'll come up with the fact that the magnetic field is pointed in the Y direction as opposed to E in the X direction, right? So there's a couple of important things that happen to be true in this derivation that are always going to be true for uniform plane waves. The first is that the electric field is perpendicular to the magnetic field, right? That's going to be always true, and it's very important to remember that. The second is that both the electric field and the magnetic field are perpendicular to the direction of propagation. Right? We have stated that the electric field is in the X direction, the magnetic field is in the Y direction, and we also said when we first set up the problem that we're just defining our axes as propagation is in the positive Z direction. So you can see that both E and H are oriented perpendicular to the direction of propagation, right? We know that the absolute value of the electric field divided by the length of the magnetic field equals eta. And we know that Vp equals 1 over the square root of mu times epsilon, the material properties, right? Now, again, I'm going to remind you, there's no conductors here. There's only materials, right? There's just, it could be empty space, it could be air. That's all that we have, right? So examining this solution, we can see that we have this notion of a forward-going wave, although in principle there could be a negative-going wave too, and F could be any shape that we want it to be, right? But whatever that shape is, it's going to be moving in the positive Z direction with the velocity Vp. But F could be a triangle, it could be a single spike, it could be a sine wave. In the next video, we're going to be restricting this to the more common case where we have a single frequency. And we're going to sort of define how the radio wave works at a single frequency at a time, and then we'll generalize from there.